Welcome class, we're talking about performing congruence transformations today. By the end of this class, you'll be able to be given a pre-image and create an image of a transformation that preserves distance and angle. We'll talk about transformations being the operation that moves or changes a geometric figure in some way to produce a new figure. The new figure is called the image. So you start with a pre-image and you end with an image. It's kind of like when I think of history, that's like England back in the 1800s, or maybe sometime around Christ, like 2,000 years ago. And then there's prehistory, which is like cavemen and long time ago, before really we had a recording or a written language to write this down. So history, it's probably when we had a written language, and prehistory or prehistoric is before we really had an idea of writing down, having sort of the written word. So that's kind of the idea with this, is that we'll start off with a pre-image, like the before image, and then our final product will be the image. The order of the vertices and the transformation statement tells you that P is the image of A, Q is the image of B, and R is the image of C. If we notice that this becomes this. So this is the original figure, or the pre-image. This becomes the image. This marking has a lot of different names in mathematics. If we're talking about if-then statement, it means implies. If we're talking about transformation, though, it basically means this transforms into this. We'll also see it written in some of the rules today. There are three main types of transformations. One is the translation, which is basically when you slide a shape, either horizontally, vertically, or both. A reflection, it uses a line of reflection, creates a mirror image of the pre-image. You'll notice usually they'll have some sort of mirror image, or it has to make reference to this line, this H, this axis right here. We'll start with the blue and turn into the red. And then the last one is called a rotation. It's kind of like a spinning something or turning a figure about a fixed point, called the center of rotation. For us, in just this basic geometry class, we'll have our origin be our center of rotation. Next, we will talk about how a congruence transformation changes the position of the figure without changing its size or shape. We'll learn another word for this. This is also called an isometry. Is a really good word, an isometry. And we'll talk about isometric transformations, or the same thing as congruence transformations. We'll start off with the first one today. We'll start off talking about translations. In a coordinate plane, a translation moves an object given distance, right or left, and up or down. You can use coordinate notation to describe it. Here's coordinate notation. If we are given some sort of coordinates like x and y, and we're moving this way to the right, some positive a value, and we'll just say x, whatever we started with, and we're going to add a to it. This is adding a distance of a. And this is y, this is where we're at in the y plane, and we're going to move up some distance of b, so that's why we're saying plus b. This shows the point x, y, and the blue figure is translated horizontally a units, that means to the right, and vertically b units, that means up. So that's where we're at. That's the notation we will use for translations. So for instance, if we're going to go 3 units to the right, first off we have to note that we're going to start with x, y, whatever it's going to be. Generically, we'll use this translation symbol here, and we'll say that x moves to the right, so it's going to be plus 3, and then we're going to move down 5. So what happens to our y coordinate? We're going to subtract 5 from it. We're subtracting because it's moving down. We're adding the 3 because we're moving to the right. Let's see how that changes for number 9. We have x, y. It's going to turn into, let's see what happens to our x. We're going to move to the left 7 units. It means we're going to subtract 7. We're going to move 2 units down. Oh my goodness, that's going to be y minus 2. There we go. The figure ABCD has vertices A, B, C, and D. Sketch this and draw its image after the translation. Boom. What means we're going to go, this means we're going to go left 3. This means we're going to move up 2. Let's see how this turns out. What's tricky about this, note if it gives you a graph that you need to work with, these are by 3s. That could make this a little complicated because I'm only moving 3 here and 2 there, but some of these coordinates are going to be kind of funny. If you're giving your own graph paper, though, you can do your own work here. you can kind of just plot these points. And I think that's the best thing to do. This is probably not a B. This is probably a C right here. So A, B, C, and D, just using those coordinates. And then what we'll do is we'll go and we'll plot these extra points on here. Each one of these points, the C, it moves over 1, 2, 3, and up 2. This moves over 1, 2, 3, and up 2. This moves over 1, 2, 3, and up 2. 1, 2, 3, and up 2. That's exactly what happened in our X direction. We moved -3 units. In our Y direction, we move +2 units. Translations. Love it. Next, complete the statement using the description of the translation. In the description, you're going to be given these 2 points and their vertices of the triangle. So if 2, 0, which is part of a triangle, translates to 4, 1, what happened to it? Well, it seems to me that there's kind of some unwritten rule here that what's going on is we're going to take our X, we're going to add 2 to it. Our Y looks like we're going to add 1 to it. So if we apply that same rule to the second vertex of the triangle, we basically have to have 3 plus 2 is 5, 4 plus 1, ooh, it's also 5. That'll be our image or our new vertex. Same thing happens here. We'll say X, Y. We'll try to discover the unwritten rule here. This is 2 to -2. That means I'm going to subtract 4. This is 0 to -1. That'd be Y minus 1. So I'll apply that same rule to this point. 3 minus 4 is -1. And 4 minus 1, oh my, that's 3. This will be our new point for our triangle, or our image of the original 2 vertices. Next, we'll talk about reflections. This is isometric transformation number 2. A reflection is shown in the coordinate plane. The line of reflection is always the x-axis or the y-axis. In this lesson, we might see it at some other points, lines, such as the line x equals 2, y equals 7, or we could even have the famous line x equals y. Oh man, maybe that's for another day. In this case, a reflection in the x-axis, remember this is the x-axis down here, that's this guy right here, the horizontal plane, and this guy is just reflected over that guy. This is the y-axis, it's the vertical, and we're just reflected over this way. Maybe we're reflected the other way actually. We're going from blue over here to the red. So let me cross that part out because that's not right. We go from blue to red. Notice that if we were looked at coordinate notation, all we're doing here is we're changing just the y coordinate is changing, and we just make it the opposite of what it started as. So if we were up here, we're down here. If we're down here, we're up here. We're just changing this y coordinate. These are always going to be opposites. Over here, notice the y coordinates here, though, are the same. We're the same amount always up or down. All we're changing is our x coordinate and our x coordinate are going to be opposites. So here, x coordinates are opposite. Just a way to look at coordinate notation. We'll take a closer look at that another day. Let's try this out. Reflections. Not a lot that you'll get for your homework. It says use the reflection of the y-axis to draw the other half of the figure. This is really boring. We're drawing the letter V. The way this works is you always start off, you try to say how many steps away from the y-axis am I? In this case I'm 0, so I'm just going to stay there. How many steps is this guy from the y-axis? Well, it's 1. So from here to here, maybe it's 2 units, but 1 giant step. So I'll put 1 more giant step here, and this will be this new guy right here. How far is this guy from the y-axis? Well, it's 1.5, really 3 units. So we'll move another 3 units this way. We'll put a dot there. How far is this guy? He is 2.5 or 5 units. So 1, 2, 2.5 is right there. So what I'm doing is I'm picking some the nice points on this graph here. And I'm just going to say how far am I from my line of symmetry or my axis of symmetry here. And then what I'll have to do is I'll just draw in the lines to connect them. Oh, this is really tough to do. Boom, something like that. I have the letter V. Most V's look like that, but this one, a little bit different. Okay, hopefully yours looks better when you're not having to do this with the mouse. Okay, rotations. This is isometric transformation number 3. The final one we'll look at. This lesson, if a rotation is shown in the coordinate plane, the center of the rotation is the origin. That means 0, 0. The direction of rotation can either be clockwise or counterclockwise. Sometimes these are abbreviated CW or CCW. CCW means we're going this away, and clockwise means we're going this away. Watch out for that. Notice it can be 90 degrees, which is a really nice amount, makes a right angle. Sometimes it doesn't have to be 90 degrees or 180 degrees. It could just be 60 degrees or 45 or even 72. So watch out for those. Notice in both places our center of rotation is the origin. Notice also that the distance from the origin is preserved. So if this distance here is maybe, I don't know, like 5 units or something, this distance here is also going to be 5 units from the origin. It's as if you're spinning your little brother around in a circle, and maybe the two of you are fighting over a shirt or something. This is you, obviously, in the center of your universe, and you're spinning him around, and he goes around and around and around, and basically this is the distance of the shirt or whatever in between. I have no idea where these things come from, but you're the one fighting with your brother over a shirt, so get over it. Okay. Use the coordinates to graph AB and CD. Tell whether CD is a rotation of AB about the origin. If so, give the angle and the direction of the rotation. Holy smokes, this is going to be tough. Okay, so we got to plot some stuff. So here we go. We plot A, we plot B, we plot C, we plot D. Is this a rotation about the origin? Well, one thing you can look at, you could say, well, this is 5 units from A to B. 1, 2, 3, 4, 5. This is only 4 units from C. 1, 2. It's only 3 units. That's even worse than I thought. It's only 3 units. There's no way that this is actually a rotation. Plus, look at B. B is like, a distance of 2 from here. It means CD would have to start here at maybe like 2. This is just a mess. This is just a big no. It is not. We should be ashamed of ourselves. Over here, we have AB. We have CD. Is that a rotation? It sure is. Which direction does it rotate? I would say it probably moves clockwise, and I would say it probably is like a 90-degree rotation. If we went from the center of this to the center of this guy, notice this is a right angle. You don't always go to the center. I just picked some nice point that I could reference as I went along. I could have picked from A to here to D to there. That's going to be a nice right angle. Also from B to C in comparison, that would also be a right angle. So check it out. Yeah, good luck figuring out angles. That'll be tough. A point on an image and the transformation are given. Find the corresponding point of the original figure. So here we go. We have this point 2, -4. Our transformation. This is our rule that we have. Basically, what's going to happen is we're going to subtract 4 from the 2. So 2 minus 4 is -2. -4 plus 3 is -1. We are done. Well, we're given this original point. We're going to use this rule now. Our x, it was an x, it stays an x. So our -5, guess what? It stays -5. Our -7, though, see how this changes? We become the opposite of y, from y to opposite of y. Y becomes opposite of y. -7 becomes the opposite of -7, which is a +7. Do you need to write the positive symbol there? No, I just did it because I'm awesome. Okay. The vertices of triangle ABC are given. Boom, boom, boom. The notation, boom, 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 describes the translation of triangle ABC to become DEF. Show that triangle ABC is congruent to DEF. To verify that the translation is a congruent transformation. Verify. This is a key term that says you're going to have to do a lot of work. Haha, work. Okay, first thing, probably graph that thing. Okay, get an idea of what's going on. Okay, so we graph ABC, we graph D, and probably EF would be a good way to do that. I don't know why I didn't do that. I just didn't do it. Okay, how do you prove things are congruent? Well, you have all those congruency statements. Remember, we had like side, side, side. We had side, angle, side. We had a whole bunch of other ones. We had angle, side, angle. We also had like angle, angle, side. We had something called hypotenuse leg, but that doesn't apply here because we don't even have a right triangle. So anyway, here's what we got. So let's take a look at this. What could we do? The first thing we could do is we could say that AC and DE are both 3. You can just look at this. 1, 2, 3. That's 3 units. 3 units. is also just 3 units. You can count them horizontally. You can see it's 3 units. Since this equals 3, that means we can say that these two are congruent. Notice we start with the length of AC, the length of DF equals 3. That means these two things are congruent. And we're talking about, hey, I just proved one set of sides are congruent. Nice. Okay, using the slopes of AB. Well, let's see. The slope of AB is up 2 over 2. So I have a slope of 1. I have a slope here of, we have a slope of 1. That means these two guys are going to be parallel. Okay, we do the same thing with AC. This has a slope of 0, rise of 0, run of 3, slope of 0. So that means these guys are parallel. Very interesting. If you extend AB and CD, you can form angle G. The corresponding angles postulate gives you that these guys equal G, and then that thing by the transitive property says that it's congruent. So basically the idea here is that because these guys are parallel lines, these become, we could say that these guys, that's going to be parallel. So that means D is going to be the same as G, A is going to be the same as G, because of the parallel lines we're working with, because they're corresponding angles. And then since A is congruent to G, G is congruent to D, by the transitive property we could say A congruent to G, A congruent to D. Pretty sweet. That gives us an angle. Side, angle, I wonder what's next. Using the distance formula then we can say that AB equals DE equals 2 square root of 2. So that means that AB is congruent to DE. Bada boom, bada boom. Side, angle, side congruence postulate. Okay, so we proved it by side, angle, side. Finally, we write some sort of statement at the end here. Because triangle ABC is congruent to da 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 da, translation is a congruence transformation. This should feel a lot like a coordinate proof. Why? Because it is. Okay, we're not necessarily stating what we're using because each one we're using is slightly different. We're kind of using the distance formula here. We're using the idea of slopes and kind of using corresponding angles postulates. Here we're using the distance formula again. Kind of feels a lot like a coordinate proof, step by step, really dissecting the math, not just saying, but it looks about right, so I'm going to say that they're congruent. No, you got to actually prove it. You got to talk about the math that helps you to figure out what's going on. Okay, that's basically all I got for you. We got these verifying. We're actually using translations, the coordinates. We're just talking about rotations. Over here, we're talking about some of these reflections, not a huge deal. Translations happen a lot because there's a lot of different ways we can look at them. Oh, I should probably talk about this notation. This is A, this is our pre-image, and this is A prime, this is our image. So pre-image is in blue, image is in red. Pre-image is just normal. The image then has the prime. So we start with B, then we go to B prime, C to C prime, D to D prime. It's another way that you'll see, hey, this is where we started. This is our image afterwards. This is what we're going to have later on. Here we're talking about some of the notation, isometry, kind of a nice vocabulary word. We got some homework. It's a little bit long, but you guys got some time to do it. Let me know if you have any questions. I'm here for you. Remember, if you're not part of the problem, no, that's not right. If you're not part of the solution, you're part of the problem, so get the heck out of the way.